This is module 10. Actually, from module 10 onwards, we will be discussing some special topics on elasticity. For instance, in this module, we will be discussing thermoelasticity, and in the next module we will be discussing probably photoelasticity, and then some elements of nonlinear elasticity in the next module. So, in these three modules, essentially these theories are very it is not it will not be fully covered in this module. So, we will give a brief introduction of these three theories. For instance, for the current module we will be talking about thermoelasticity. So, thermoelasticity or thermomechanics itself is a subject. So, what we will try to discuss here is that the basics of thermoelastic deformation here, and with some given assumptions that is helpful for our systems. So, in general we all know what is the effect of heat in a structure. So, for instance, if I heat a steel bar or steel rod, it is we know that it expands, and this knowledge is coming from our strength of material knowledge. So, we have seen that the strain is essentially, if the length of the bar is L, then coefficient of thermal expansion, that is alpha, then the change in temperature, that is delta T, is related to the strain of the bar. So, this strain is essentially can be converted into the change in length, which is delta L. For instance, if the bar is of length L, so delta L by L is the length, and how it is related to the coefficient of thermal expansion and the temperature rise or decrease. So, this was our initial concept of thermal effect on an elastic structure. So, here we will start with that and then slowly define what is the thermoelasticity, or what kind of thermoelasticity we will be considering here. For instance, in our introductory lecture, possibly I have told you that we will be mostly interested in uncoupled thermoelasticity, where the heat and elastic behavior are not communicating each other. That means there is the two types of differential equation. For instance, heat, if I heat a body, so heat is propagate from one end to the body to another end of the body, and this physical phenomena can be modeled by the heat equation. And similarly, if I give a load to a structure, then this structure is deformed, and this deformation is modeled via the elasticity equation, which we have discussed till module 9. And now, if there is a heat, then also there is a stress generated. For instance, so basically thermoelasticity is nothing but elasticity behavior of a material due to temperature change. So, that is the thermal effect on an elastic body. So, for instance, we have seen the mechanical loading, what is the response of a elastic body if I give a mechanical loading to the body. Now, we are discussing what is the response of the elastic body if there is a change in temperature, or the thermal loading specifically. For instance, if I this is a bar, for instance this is a bar, and this bar, if I want to heat it uniformly, so now there are some assumptions that this is this uniform heating and all those things. So, if I heat it, it will expand. So, what will happen if I heat this bar to a uniformly to everywhere in the bar? If I heat, so this bar will expand like this. So, now the question is, if there is no mechanical loading, will there be thermal stress generated? So, the answer is no, because it is freely expanding. So, there will be no thermal stress generated. But for instance, if I restrict the bar at one end, then there will be thermal stress, because the bar is now not freely expandable in this region. So, that is why this uniform heating will generate a thermal stress in the body. So, this phenomena actually we are trying to model. So, essentially what is this, why this thermal stress is generated? Because there is a the bar was in a normal, say, room temperature, and then you heat through a heating source. Then this heating source will create the change in temperature in the body compared to the outside temperature. Now, this temperature change will generate stress, and also we know that if there is a constraint or there is a restriction of expansion, for instance this case, if there is a restriction of expansion, then only it will generate the stress. But if there is a no restriction of expansion, for instance if I remove the constraint here, that is a built-in, and here, then the bar is free to expand and there is no thermal stress generated. Now, this is very similar fact to a rigid body motion. For instance, in a rigid body motion, if there is a in case of a elasticity, purely mechanical loading, if this bar is for instance this is a bar, and then you give a load here. So, this bar or you give beam or bar, whatever it is, you give some load here. So, what will happen to this bar? This bar will move freely in space. So, this bar will be somewhere here. For instance, this bar will be somewhere here. So, with this, so the each point in the bar is translated and rotated. So, it is not a deformable motion, it is a rigid body motion. But if I give a constraint to the bar, for instance similar to this, then only the deformation is generated. So, the similar the concept the thermal concept of thermal stress here is very similar to that. So, here only the constraint I am introducing, and then only thermal stress is generated. So, this effect we will see how we can mathematically model this thermal effect on a elastic body. So, to start with, we will be discussing what are the basic things or the basic principles by which we will start our modeling. So, for instance, this the example of thermoelasticity is in our everyday life. So, I will not discuss much about these things. These things are very common to our life, and we know what the thermoelastic effect is. For instance, the dual composite bar with a thermal heating effect, and which is used in every system that we are using. So, now let us also review what is the thermal stress if I heat a bar uniformly. So, for instance, this is a bar where I have not fixed this bar at the one end, then I try to heat this bar. Now, this is from our strength of material knowledge, we know this delta L, which is essentially the increase in length, is alpha L delta T. So, the strain is essentially delta L by L. So, this we know. Now, from our if there is an equivalent loading of suppose there is an equivalent loading equivalent force which is F. So, also we know that this equivalent load if I put here, then the strain will be generated is FL by AE. This is also we know from the strength of material knowledge. Now, so I can write simplifying F, I can write in this manner. Now, if I want to compute the stress due to this heating, this thermal heating, then I just simply know the one dimensional stress formula is force by area. So, force I know, area I know of the bar. So, which comes out to be E L delta L by L. So, which essentially again comes out to be alpha E delta T. So, you see the stress is actually involving the elastic constants also. So, that is how this response of a elastic body due to change in temperature. What is this delta T? Delta T is the change in temperature and alpha is the coefficient of thermal expansion. So, now it is important, this simple example shows us how stress is actually related with the thermal coefficients, that thermal property of a material as well as elastic property of the material. And why it is happening? It is happening due to the change of delta T. So, change of temperature, that is delta T. So, this is the basic principle we need to understand before we proceed the more complicated 3D behavior of a elastic body under thermal stress. So, now let us see what kind of this is a simple example. For instance, if a mild steel bar at 300 degree Kelvin is clamped between two walls, calculate the thermal stress of the bar when it is heated to 350 degree Kelvin. Now, important fact is that there is we observe thermal we observe temperature changes, but if this temperature change is significant or it depends on the material also, so then the thermal stress is not negligible. We need to compute the thermal stress to account for the failures of the to prevent the failures of the structural body or the material. Now, if the Young's modulus is 200 GPa and alpha is the coefficient of thermal expansion, which is expressed in per degree temperature, that is per degree Kelvin here or per degree centigrade or Fahrenheit, any unit you can use. Now, if I want to calculate the thermal stress, I will just simply use that this E alpha delta T, which comes out to be 112 MPa. So, this example shows that even if you use for a small mild steel bar, it depends on the how the alpha and delta T as well as the property of the material, that is the Young's modulus of the material. So, the stress that will generate by heat change in temperature is dependent on the elastic body itself. Not only that elastic body, the elastic properties of the body as well as its thermal property. So, this is the main thing that we are looking for here. Now, for instance, what is heat transfer? For instance, if you boil a pan of water, then what kind of heat we get? So, for instance, if I heat it, so there is a source of heat is going to the surrounding through radiation. So, radiation is transfer of heat by emission of the electromagnetic radiation. So, this we call radiation. So, we are not interested here right now the radiation heat transfer. So, now there is another thing which we observe. If there is a if I start heating this pan with water, and then the water molecule will go up and down, and so this will also release some heat. So, where this heat will go through the surrounding atmosphere. So, this process is also known as the convection process. So, the transfer of heat through movement of fluids, this is the convection process. Now, another observation we can made it from here, that if I touch this bar, so will fade this handle of this pan, then we feel that it is heated, because this heat is actually propagated here. So, this is known as the conduction, the heat conduction. So, transfer of heat, when transfer of heat happens to a physical contact, then we say it is a conduction. Now, we are mainly interested in the conduction, heat conduction. So, for instance, this another example, simple example of heat. If you in a candle, if you put a metallic rod or metallic bar and touch it, so heat flows from this side to this side, and this actually happens through this metallic bar, and so you experience the temperature change of your finger. So now this property, or this is the basic physical phenomena that we are interested in. For instance, how heat flows. So this is governed by the basic Fourier law of heat conduction. So what it states, the main purpose of this heat conduction is that how Fourier law is the how heat will flow of heat in solids associated with the temperature difference. That means that how in a solid heat will flow from one body to another body, one part to another part. So we all know that the higher temperature side, the heat will flow to the lower temperature side. So now if consider a simple two-dimensional body where there is a this boundary there is a temperature is T plus delta T, and in the this side the temperature is T. So it is natural from our physical observation, as our intuition, that heat will flow from this side to this side. So heat flow is modeled as Q dot. So Q dot is the heat flow. Now naturally Q dot is if the temperature is more here, so this side, the opposite direction, the heat will flow. Now what are the assumptions on it? So the assumption on it that there is a steady state heat conduction. What this steady state means? That is, there is no fluctuation involved. So heat is flowing in a steady state. So that means there is no transient, or there is no change of heat flow. So and it is one directional flow here. Now another important thing is that compared to the realistic situation, that this side the always temperature T plus delta T is maintained, and this side always temperature T is maintained. This is known as the isothermal character or isothermal property. So all of these things we know. Now so these constant temperature gradient, that means linear profile, all these things we will see, and there is no heat source into it. So in this body there is no heat source, or there is no externally supplied heat into the body. Now when we violate these conditions, then this governing Fourier law of heat conduction does not apply even. So we will first assume this quantity or these assumptions, and then we will derive what is the, or we will see what it looks like Fourier law of heat conduction. For instance, the Fourier law states that time rate of heat transfer through material. So time rate means that heat transfer over time and its rate. So basically the heat transfer is, if it is Q, then dQ by dt. So is the heat transfer. So time rate of heat transfer through material is proportional to the negative gradient in the temperature. That means why negative gradient? Because you see the heat, the temperature is higher this side and lower in this side. So obviously it is going in the opposite direction. So that's why it is negative. So that means dq, or if I write in a differential form, dq by dt is proportional to the gradient of the temperature. That means what is the gradient of the temperature? Gradient of the temperature, if one side it is T plus delta T, another side is T. So T plus delta T minus T by delta x. So why delta x? Because the path by which it is flowing. So this is proportional to del T by del x, and then it is also dependent on the area of the section. So, that means it is also proportional with the area of the section. Now, as this is a proportional quantity, so to make it equality we need to have a constant k. So, this constant k is known as the conductivity or thermal conductivity of the material. So, that here the material property comes into where the heat flows from one side to another side. So, material property of the comes into picture here. There depending on the thermal conductivity of a material, the heat flow will be different. For instance, if I use the wood and if I use the steel, the thermal conductivity from one side to one side, that means the thermal conductivity of wood and thermal conductivity of the steel is different. So, heat flow will be different. So, this relation is actually known as the Fourier law of heat transfer. Now, if I say now that the Q by A is a quantity which I consider as a heat flux. So, that Q dot by A, if I consider, that means heat flow per unit area is known as the heat flux. So, this heat flux if I write from here, so it is the K into dt by dx. So, in a one dimensional case I am using this. Now, in a 3D obviously I can extend it for 3D, which is then Q will be your a three dimensional quantity, and K the conductivity. Obviously, as we have seen for elasticity case, conductivity will be a conductivity tensor. For instance, it is a second order tensor. Now, similar to the elasticity case. Now, dt by dx will be the gradient will be in terms of three spatial coordinates, dt dx, dt dy, dt dz. All those quantities will come. Now, this conductivity again, for instance, in an isotropic material where the material properties are same in all directions. So, there this conductivity does not depend on whether it is x direction or the y direction or the z direction. So, this conductivity will be same in the x direction, y direction and z direction. So, I can write K ij, that is the conductivity tensor, is a diagonal tensor, which is K into delta ij, right. So, these things we know. So, if I now put it in a one dimensional setting and in initial notation, it looks like this. Now, so this will be bold. So, now this is the basics of Fourier law that we are interested in. Now, let us see how these things works. So, for instance, wall of a industrial furnace is constructed from 0.1 meter thick fire clay brick having thermal conductivity of 1.7 watt per meter Kelvin, and temperatures at the inner and outer surface is 800 and 500 degree Kelvin. So, calculate the rate of heat loss through the wall having cross sectional area 0.06 meter square. Now, so what is dx? Dx is 0.5. Now, this is 800 and this is 500 and area is 0.6 meter square. So, if I just can compute the heat flux is essentially conductivity, which is 1.7, and then del T by del X. So, del T is your 800 minus 500, 300 degree temperature change, and del X is 0.15. So, this gives me the heat flux 3400 watt per meter square. Then rate of heat loss. So, heat is from this surface to going to this surface. So, this surface will have a heat loss. So, which is Q into A. So, that is 3400, which we have got from the heat flux multiplied by the area. So, 2040. Here you see you have not used sign. So, we know that heat loss, heat flow, that is in this side. So, that is why we have not used the sign. So, now let us see how this happens if there is a differential temperature setting. What does differential temperature setting means? That means I have in the beginning, as I have told, that if I have a simple body, and then this simple body starts we start heating, then at a position of a body, for instance this is a bar, and this bar I am trying to heat it. So, if I heat from here, then the heat will propagate from this side to this side, and then this will give rise to the temperature also. So, this is actual phenomena, the real phenomena is occurring in the physical body. So, how do we model that? We model that via heat equation. So, heat equation probably you have learned it. So, here what we will do, what are the principles that is required to derive this heat conduction from one side to another side, and what are the laws involved it, and we will derive it for a one dimensional simple case, and then you can extend it to for three dimensional case very easily. For instance, suppose a metallic rod with non-uniform temperature, with non-uniform temperature, heat is transferred from higher temperature region to the colder, the lower temperature region. So, then to derive heat equation, what are the principles we need? We need the heat energy, what is the heat energy expression, and we also need the, just we have learned the Fourier law of heat conduction and the conservation principle, similar to the elasticity case. So, now heat energy is can be written as the specific heat C, m mass, and T is the temperature. So, the energy into is the specific heat. We know the specific heat is to raise the temperature of a unit mass, what is the energy required, that is specific heat, and if mass is m, so we can compute the energy, and there is a temperature. So, this is essentially the heat energy. And now, similar to that Fourier heat conduction, I also know that Q, my heat flux, is conductivity K, and then dt dx, the temperature gradient. So, now what is left? What is the conservation principle? What is the conservation of heat energy? Now, here before discussing the conservation principle, we also we also have to have the assumptions invoked into it. What are the assumptions? And the assumptions are, for instance, if I start heating this bar from this point, so these there is a insulator this side. So, these insulators will not allow me to lose the heat from the boundary of the bar. So, these are essentially assumptions, because otherwise we cannot derive the equation, because then we have to consider the radiation, all heat transfer, all phenomena involved into it we have to consider, and then we can consider slowly, we can release these assumptions and then consider the actual case. So, we will not discuss in detail all those actual cases here, but rather we will discuss more simplified way of how to derive the heat equation, which is very commonly used. Now, the heat energy we know Fourier heat conduction. Now, conservation of energy. For instance, if I now consider a point here which is say which is x, and then at a certain distance del x, it is x plus delta x. Now, this is delta x. So, now here this delta x, or this is delta x. Now, what I assume based on our assumption is that temperature in this field is constant, because it is a very small element. So, like we have derived all our physical laws. So, this temperature here is constant. Now, so, the spatially constant, I mean constant means it does not depend on x. So, what change of heat energy, what conservation principle I have to follow is the change of heat energy. That means here in this zone, what is the change of heat energy will be heat from the left boundary, that is from this boundary, and heat from the right boundary. So, that means heat which is entering from the left boundary and which is going through the which is going out from the right boundary. So, this is the basic conservation principle that we need to follow. Now, similar to our previous heat equation, heat energy expression. So, what is the heat? For instance, the here the time lapse is delta t. From here to here the time is delta t. Now, that means t at x plus delta t, x comma t plus delta t should be multiplied with the mass, that is mass is rho a into delta x. So, what is the this is the density and this is the length and this is the area, which are all constant. I assume k is also constant, c is also constant, or specificity is also constant. So, now so my heat energy at time t plus delta t will be the Cp rho a delta x t in t of x t plus delta t minus Cp rho a delta x t a of x comma t. Now, this will be my total increment of heat energy, delta increment of the heat energy. Now, which should be the heat from the left boundary and minus heat from the right boundary. So, heat from the left boundary is delta T A into Kx. So, this is over time. So, this is Qx, Q at x, that is Q is the heat flux. So, total heat is A into Q, we know from Fourier law. So, similarly delta T A Q at x plus delta x, which is again from the Fourier law. Now, if I now expand it and if I just use our differential form, then if I after doing some modification we can get the heat equation. For instance, if I now use this equation and then I substitute q equals to minus k delta t delta x, which is the Fourier law, and then k minus k delta t delta x at x minus k delta t delta x at delta x, x plus delta x. Now, after some manipulation we get this coefficient, and this is the quantity and this is the quantity I get. So, this is coming from here after some manipulation. So, just put delta t down and then delta x down here, and then a is cancelled from the both side, and this will give me actually, if I now make delta x tends to 0 and delta t tends to 0, then I can use the partials. So, this quantity becomes del t by del small t. So, what is del t by del small t? It is the change in temperature. So, now change in temperature over time. Now, then this coefficient I am saying this is alpha, which is known as the thermal diffusivity, or K by Cp rho. This is known as the thermal diffusivity, and then this is the spatial derivative, or del square t by del x square. So, this is nothing but the second derivative. If you know the finite difference, the from the forward difference thing we can find out. So, now here this is the one dimensional heat equation that we need to solve. Now, this is the governing differential equation. A differential equation is not complete unless you specify the boundary conditions. For instance, this is a time dependent differential equation. So, you need to specify boundary condition as well as the initial condition, that means time dependent conditions. So, this can be specified depending on your problem. The specification first can be of Dirichlet boundary condition or the your temperature dependent boundary condition, then it can be flux dependent boundary condition, and then it can be mixed boundary conditions also. So, all those things we will not discuss here. So, it is just the purpose of this thing just to introduce you that there is a heat equation involved which actually capture the heat propagation from this side to this side, and this equation actually tells you what is the temperature from one side of the body to the another side of the body. For instance, if heat is propagated from here to here, then what should be the temperature, and this is governed by the heat equation. Now, this can be also done extended from 3D, and 3D heat equation looks like this. So, there is a the dt by dx, dt by dy. So, these terms will come. So, this equation, this is a basic heat equation. Now, this can be modified for a radiation and all those things. For instance, if you want to use a radiation, then some term will be deducted from this equation. So, all those things can be incorporated in the heat equation. So, the basic objective of describing this thing is that the heat equation is governed from in the material, and this heat equation, the purpose of heat equation is to know from which side to what is the temperature profile from this side to this side of the material. So, because in elasticity, when we will solve the effect of thermal stress on elastic material, we need to know the delta T. So, how do you find delta T? Actually, you need to find it from the heat equation. So, this was the objective. So, I stop here in this, and in the next class we will start the basically the general uncoupled form of elasticity, thermoelasticity. Thank you.